All right, welcome to the roast of Michael Froh. In all seriousness, I do need to poke fun at you a little bit. 2 years ago at an OpenSearch Con unconference, my friend Mike here gave a lightning talk at the unconference, and the entire content of the talk was, OpenSearch is not a database, fight me. And yeah, these are designed to be like interactive sessions, so it was a little aggressive, Mike. And then last year he followed it up with another talk, and the entire content was OpenSearch is a database?
Yeah. Now, in my defense, I didn't entirely contradict myself. That first talk was more about like, don't use OpenSearch as an online transaction processing system. OpenSearch and Lucene are not really meant for strong read after write consistency, that there is some inherent eventual consistency there. But the second talk was more about OLAP systems and what can OpenSearch learn from the database world to be a more efficient analytics platform. And that's mostly what our talk today is about.
Yeah, so we all love OpenSearch for its fast, full-text, numeric range, and vector search, but what can we do better? And we think we can do better when it comes to running analytics on larger data sets. So today we're going to talk about some experiments we've done bringing in a vectorized query engine, DataFusion, inside of OpenSearch to run alongside Lucene. So first we're going to kick it off by describing what DataFusion is and how it's built on Arrow. Then we're going to go into some use cases to apply this into OpenSearch, specifically for aggregations, and then we'll look at some ideas we have for implementing joins. Then we'll look ahead at some architectures we think this unlocks using DataFusion. But first, who are these people? My name is Marc. I'm a core maintainer on OpenSearch. My main contributions to the project thus far have been segment replication and more recently reader-writer separation.
Yeah, and I'm Mike Froh. I'm also a maintainer on OpenSearch Core. I'm also a Lucene committer. My major contributions to OpenSearch have been search pipelines, and I did the initial pretty buggy implementation of the wildcard field type, but luckily some folks over at ByteDance came along and fixed all my bugs. So it's great now. And on top of that, we both like barbecuing, and we meet for beer after work most Fridays.
Yeah, it's not lost on me that happy hour is soon.
Yes.
Also, there's 3 people on these slides. My son couldn't make it. He's at home watching Bluey.
So
you're up.
Okay, so the first building block that we want to address is Apache Arrow. I was trying to come up with a good overview of what Arrow is, and finally I just went to the Arrow website and stole their overview. So the key takeaways, from this sentence that I copied. So Arrow is an in-memory format. It works very well over the network, not really meant as a storage format. Like you don't write things to disk with Arrow, generally. It's language independent, which is important for us because DataFusion's written in Rust and OpenSearch is written in Java. So the fact that Arrow allows us to seamlessly integrate these without copying any data. Like it's a zero copy format. And the key word here is probably columnar. So it's a columnar data format. So what does that mean? So let's imagine you've got this little row of data, or sorry, this table of data. A natural way that you might write this would be to go row by row, right? Because that's probably how you're inserting the data, row by row. But instead, Arrow breaks things down into columns. Right, so it goes down the name column, then the age column, and finally the pet column. Why is this useful? Well, usually a lot of processing is done on columns. Like, if you have a where clause or a filter, then yeah, you're usually filtering on a specific column or field. So you can imagine, let's say you're doing a range query over the age field. Because these are stored contiguously, you could load multiple age values into a CPU register, and then using a SIMD, single instruction, multiple data instruction, you could filter multiple integers with a single operation. And modern CPUs make that really fast. Now, some of you may know Lucene and be saying, But Michael, isn't Lucene already columnar? It's like, well, yes. The distinction, what the main difference that I want to highlight is Lucene, I would argue, is completely columnar, at least within a Lucene segment. When you write doc values in Lucene, it's generally, here's a field, here are all the values for that field, and then you move on to the next field and all the values for that field, etc. Whereas Arrow breaks things down into these record batches. If you're familiar with Parquet, you might also call them row groups. By default, Arrow, I believe, uses 8,192 rows in a record batch, but you can tune it. Again, comparing to Parquet, I believe the default for Parquet is 1 million rows in a row group. Anyway, so the value of this in not being completely columnar is that in general you do kind of want to alternate a little bit between processing a column of data, but then also maybe filtering another column. So if you're doing that with Lucene, you potentially have to have multiple pointers into very potentially far apart locations in this doc values file. Whereas with Arrow, within a record batch, a single record batch has a series of rows. And so, if you have to filter across multiple columns, you can without going too far. This data locality probably isn't, you're probably, even with Arrow, not close enough to really make a difference in terms of CPU cache lines, maybe. But if your data is stored on remote storage, this is something where Lucene, you potentially have to be reading chunks from different parts of a file, whereas with Arrow, it's like, oh yeah, it's all there in the record batch. For more information on Arrow and the integration of Arrow into OpenSearch, I definitely recommend that you check out Saurabh and Vamsi's talk tomorrow at 3:40 in the Gold Room.
All right. So let's introduce DataFusion. So I also found the best definition of it on its website. It's an extensible query engine written in Rust that uses Arrow as its in-memory format. In fact, it was born out of the Arrow project several years ago. You can fully customize it. It's a query engine out of the box, so you can fully customize it at each layer. Where it's being used today is more as like a toolbox for building new databases, where you don't have to reinvent the wheel from the top down. It's also being used as a query accelerator, where you effectively rip out your existing query engine and drop in, replace it with Apache DataFusion. You may be familiar with the Spark accelerator, Comet. Now, I know what you're thinking. OpenSearch already has a query engine in Lucene, and we love Lucene. We're not looking to replace it. We're looking to introduce this as something complementary to work alongside it. So out of the box, DataFusion comes with data source support and file format support, like Parquet, both locally and over the network in an object store. It comes with a language front end, a SQL parser, and a nice data frame API, so you can programmatically build your queries. And of course, being a query engine, it comes with a planner, optimizer, and the engine itself. Where I'd like to focus is how it's extensible in terms of data sources. Yeah. So let's look at how we would actually implement a new data source for DataFusion. So it comes with an interface or trait in Rust that is the table provider that's intended to define a single queryable table. You can roll those up into a schema and then a catalog similar to typical database terminology. How this looks is you effectively have to define the provider itself, and in its scan method, return a physical plan or an execution plan to then fetch data from your source. So thinking ahead, what we're looking at doing here is defining our own table provider to fetch data out of OpenSearch. And that's what we did in our experiments. We're also when we do talk about aggregations, we are using a community-built flight table provider in order to fetch data over the network. So before we go into how we're applying this to aggregations, Mike's going to talk about how ags work today.
So actually, before I talk about how aggregations work today, let's first talk about how just search requests in general work on OpenSearch, just to get all on the same page. That a client sends a search request to a node. For the purposes of this search request, that node takes on the role of coordinator, meaning that it will coordinate the rest of the search request. And it does that partly by fanning out to shards on data nodes. It sends what are called shard search requests. Each of the data nodes then does the real heavy lifting, sends back a shard search response, which then the coordinator reduces into a single search response that it sends back to the client. There may be multiple phases where the coordinator calls out to the shards. If you're actually searching for documents, then it will first fan out to the shards, get back matching doc IDs. The reduce phase collates them and takes the top docs, and then it goes back to actually fetch the documents themselves. But since we're talking about aggregations, that's usually actually just done in a single phase, that the query phase takes care of everything. So the key takeaway though that you need to get from this slide is the fact that the coordinator really doesn't do a lot. Like after it fires off these shard search requests, it's mostly just waiting. And that final reduce phase is pretty cheap. So let's look at an example of an aggregation running at the data node level, because that's where all the action happens. We're going to consider this eggs request, where we're querying over people aged 18 to 35, and we want to aggregate to see what kind of pets they have. What are the most popular pets in this age range. So first we're going to run the query. Well, we're filtering on the age field, so we have to read that field. This range query gets applied to that field, and it's not too hand-wavy to say that essentially the range query returns a bit set. It really is a bit set that comes back from a sufficiently large range query. So this gives us the matching doc IDs, and then now based on these doc IDs, as we step through and collect these documents, the aggregator will go and read the pet field, which looks kind of like this. Now, these numbers might actually appear to be very, very strange looking pets, but in fact, they're just ordinals into a dictionary that was constructed at index time. Now, from this dictionary, we know what the maximum ordinal is. It's 6, and because we're real programmers, we count from 0. And so we allocate an array of size 7. And then, as we step through the documents, we just read off these values and increment the bucket counts. So yeah, that's in a nutshell how the aggregation works. And then finally, before we send the response back to the coordinator, we have to go and do the dictionary lookups because these ordinals are going to be shard specific. Technically, the ordinals are Lucene segment specific, but within the shard, there's this thing called global ordinals, where all the per segment ordinals get merged together into one big dictionary. So I'm not hand-waving too much, pretending there's just one dictionary. In a way, there is. So what's the downside of the way that the data nodes do all this work and do all the heavy lifting? It's like, well, so I wrote out these bullet points mostly to make sure that I remember each of the steps in my argument. That aggregations do all their work on the data node. Those arrays that are used for the aggregation are allocated on the Java heap. And that example, okay, it's a little array of size 7, that's nothing. But you can imagine, if the cardinality of the field is really high, you have to allocate a bigger array. Most people aren't just doing one aggregation per request, they're often doing a bunch of nested aggregations. The number of buckets can potentially get very, very large, and when you nest aggregations, you're generally doing a cross product of the buckets. Or a Cartesian product of the buckets. And so the number of buckets gets very big to the point where aggregations are a major driver of heap usage on OpenSearch. Lucene itself actually uses almost no heap. It's at search time. It does use heap for indexing, but at search time, Lucene uses almost no heap. It's really efficient. Now, of course, to avoid running out of heap, you allocate a bigger heap. Well, but you allocate a bigger heap, and the JVM is taking that memory away from the operating system, which means the operating system doesn't have it available to cache files. And when you're not caching files, it means that you have to read the files from disk, which of course is really slow. So that's, in a nutshell, the problem that we're trying to fix. And for more details on memory usage on OpenSearch, and this whole question of like how much heap do you allocate, and the implications of garbage collection on your heap. Check out Marcel's talk. Marcel's in the audience today. That will be in this room tomorrow at 2:40. It's going to be a really good one. So, Marc.
Hi, me again. So let's go back to our table provider and see how this is used with OpenSearch. So remember, we wanted to find essentially an execution plan that when we call execute, goes into OpenSearch, executes a query, and gets values back out of it in the form of arrow. So once we have an implementation, we can use it like this. We basically register it on a session context, which is like the entry point for executing queries and defining configuration. Notice we have our pets index here, and we pass in the schema. And then we can execute a query against it. When that is run, it looks like a typical logical plan, right? And I want to draw attention to the scan node where we're pushing down the filter and projection that we will then translate into a Lucene query or query into OpenSearch during that execute call. This is another look at what that scan actually looks like. You can see our range filter here for the age of 1835, and then the projection that we only care about the pet column. So let's zoom in a little bit more on the execution side. So how we envision this working is that during that execute, we then call back into OpenSearch over a JNI boundary. We will have to pass DSL. So if we are starting with SQL, we will actually have to translate to DSL and execute it as a Lucene query. What we do today is that we call collect in a collector for each doc ID. What we'd be doing in the future is effectively collecting all of those doc IDs into an array, and then when we've completed a batch, we'll translate that, do the actual doc value lookup per field, and write those into separate vectors that we will then send back to DataFusion. This is what that actually looks like. When we get that arrow buffer back, you might recognize these ordinals that Mike introduced. You might also be thinking, how do we translate these back to their text values? And we can define that dictionary, that same dictionary he was talking about, when in our collector when we're defining our vector schema with arrow, and then DataFusion will know to automatically translate those back after it's computed all of the buckets for our aggregation. So yeah, let's zoom out a little bit and see what this would actually look like on a data node. So the entry point would be our DataFusion execution engine. We'd again go over that JNI boundary, go into Lucene, which would actually do the query and then fetch doc values, right into arrow and give them back using zero copy. But you can imagine when we zoom out and look at this cluster wide, we're looking to achieve the goal of lifting some of that work that Mike was referring to off of data nodes and putting onto collectors. All right. Everybody good? Okay. Yeah, pulling some of that work off of the data nodes to be done at the coordinator, rather. And I introduced that flight table provider earlier. In our experiments, what we did was we plugged this in and then treated each shard in the index that we were querying as a separate partition. So yeah, that's how we got that to work. So we've done some early experiments with this, and we think that it is really promising. We saw about a 30 to 35% reduction in latency for a terms aggregation that we were running through the Big 5 workload. This is on a 3-node cluster, so you can configure your cluster any which way to make benchmark look good, and that wasn't our goal here. Like, we wanted to take something like out of the box, so we didn't tweak any heap or anything like that, heap sizes, but we could also tweak it, like he mentioned, we could reduce the heap size at the data node to add more like OS file cache capability, but this was just straight default settings. And then, yeah, we saw like the P100 heap utilization drop pretty significantly. Yeah, so I'd like to link to an RFC where we introduced this idea and linked to a whole bunch of code that you can look at if you're curious, and we'd love feedback on this. So yeah, Mike's going to talk about joins.
Yeah, cool. So the eggs use case, as Marc said, we did some experimentation. That's a real thing that, again, there is some code. You can kind of run it. You can kind of. Okay. Yeah. Joins have been more of a topic of discussion. That we've said we could do joins. So this is going to be a little bit more theoretical. So first, let's look at how do joins work today on OpenSearch. Well, generally, you want to have the SQL plugin. So once again, you've got your client, your coordinator, your data nodes. Here I've called out some specific shards because I want shards from 2 different indices because I'm going to join them. So we've got Pung in the audience today. He's essentially Mr. SQL plugin. So hopefully I'm not going to butcher this too much because he'll be able to beat me up afterwards. Anyway, so I'll do my best. So the client sends a SQL query to the SQL plugin, something like this, doing a simple join between customers and orders, sort of your standard SQL join example. We're filtering both on the customers and on the orders, and the SQL plugin takes the query string, turns it into a plan that will look something kind of like this, that we're going to do index scans on both the customer and order indices, and then finally we're going to do a hash join over the resulting documents. This index scan, we can take the where clauses that are restricted to one index or the other, and well, we can turn those into a DSL query, which then just gets pushed down. And this is, as I understand it, what the SQL plugin does. It just gets pushed down, runs these queries against the 2 indexes, either scrolls through them, or I believe now it uses the search after API to sort of paginate through all the results. But as I understand it, the full hash join actually runs on the coordinator, where the size of the hash table to do the hash join could get quite large. And this is part of the reason why there's the OpenSearch Spark plugin. Well, I guess it's not a plugin. Well, it is a plugin. But the whole OpenSearch Spark system allows you to offload some of these heavier SQL queries to a Spark cluster. The downside is you then have to set up a separate Spark cluster. So let's zoom out a little bit and think about like how could we handle this within a cluster using DataFusion. Well, when we say that the coordinator's hitting these 2 indexes, remember, an index is just made up of shards, right? So when we join the customer index with the order index, here in my picture, I'm assuming the customer index has 2 shards, order has 4. Obviously, these numbers are usually going to be much bigger, but it's hard to fit 1,000 shards on a slide. So what really ends up happening ultimately is that the coordinator is really kind of joining every customer shard with every order shard, right? So you can kind of think of your join here as really being 8 mini joins. Well, what if, hypothetically, we could introduce some additional, probably coordinator nodes. I'm just calling them coordinator nodes because I want to assume that they're not holding any data. These are purely compute, right? And we're going to designate them as workers for the purposes of this request. And maybe what we do is each worker takes one of the order shards and joins it against the 2 customer shards. Actually, I was out for a walk before the talk, and it dawned on me, you should actually probably do it the other way around, that you should probably join one customer shard because you're joining on its primary key, that you're guaranteed that if you just take one, then you're reducing the hash space by a half. But anyway, I didn't have time to redo the slides. Anyway, so let's imagine how this might look with DataFusion. The idea would be that the coordinator would still have the SQL plugin there, still receive the SQL query. The SQL plugin would construct a plan, but that now this plan would be DataFusion aware. And so we take this top level query, and for one of the workers, we would push down a query where we've restricted, I've done this little sort of square bracketing notation to indicate which shards are being hit. So let's imagine the worker's hitting both customer shards and a single order shard. And then that worker would then push down work to the individual data nodes, where at this point you're just doing your filtered or your index scans on the individual shards. And all of the communication between nodes is still these flight providers. Down at the data node, this is where you're using your OpenSearch table provider to execute these shard level queries. And then we just stream the results back over the flight stream, do a mini join on the worker, and then once all the workers have completed their mini joins, they pass their partial results back to the top level coordinator, which then just has to merge them. So we can divide up the work. Now, again, we haven't done this yet, but theoretically DataFusion should make it fairly easy, right? Like we could implement something like this in OpenSearch in Java, but it would be we'd have to write a lot of code, right? Whereas theoretically, DataFusion just gives it to us. So that's the vision, at least.
All right, so to recap, we talked about aggregations, we talked about join use cases. We think we can do more with this. So imagine you have, for cost effectiveness, you've got data stored in a Parquet file on a data node next to your Lucene index. We could theoretically join doc IDs out of Lucene with that Parquet file. Or imagine that file's on an object store or in an entirely different data system. So we think this unlocks some pretty interesting use cases, but there's a lot to do here to bring this into OpenSearch. I borrowed this slide from a colleague because I think it shows like the amount of new things we're looking at introducing into OpenSearch. I didn't even touch on the top left today in terms of query planning with Calcite. I know there's work going on, again, Pong within the SQL plugin to implement Calcite. And the general vision there is to use that to translate into a portable IR format for our logical plans so that we can pass off to effectively any engine. I know we talked today a lot about DataFusion, but theoretically, if it can read those plans and operates on Arrow, we could substitute in or drop in another execution engine in the future. So how we're looking about introducing this is with this composite engine concept, where based on your index configuration, we know where to go to execute the query, whether it's Lucene like it is today, or whether it's this off-the-shelf engine. So I mentioned there's a lot of work to get this in and get this going. The key thing here is OpenSearch is tightly coupled to Lucene today, and rightfully so, right? We love Lucene, but it's everywhere. Like just encapsulating all of it and swapping in a new engine is difficult and time consuming, but we have some ideas of how to do it. But there's other problems, right? Like how do we configure types? How do we connect index mapping to arrow schema to the schema in DataFusion? How do we format responses out of DataFusion, right? Like we'd get arrow arrays back, but then, vectors, but then how would we convert those to the JSON response that users are used to today? And then particularly with joins, how do we implement that like breaking apart of the plan, like distributed planning, in order to execute fragments on different data nodes? So there's a lot still yet to be done, and we'd love participation and help. There's 2 RFCs I've linked here if you'd like to get involved. The one on the left is more of the high-level idea of this, and the one on the right is describing the search path in a little bit more detail and ideas of basically what I mentioned about like planning and execution down to the like specific engine implementation. So yeah, thank you, and any questions? I see one over here.
I have 2 questions. First
Sure.
I can yep. So our vision is that this would provide opportunities to enhance the SQL plugin. Ideally, as a user, you wouldn't be able to tell, right? That this would be something that we would implement internally. That once we have DataFusion running on all the different nodes, then it just becomes something where the SQL plugin, as part of its planning and execution, is able to then offload work to DataFusion. Largely, again, what DataFusion's giving us isn't necessarily that it's a better execution engine. It is kind of like it, the fact that it's able to natively do a lot of these SIMD operations over the Arrow data is really nice, because it is kind of hard to do that in Java. Doing SIMD operations in Java is not great these days, whereas DataFusion written in Rust can just do it with the SIMD intrinsics. So that's part of it, and then the other thing is, as Marc said, it's a toolbox, right? The fact that it exists, right? That if otherwise we would have to re-implement all this stuff in Java. So, yep.
Yeah, I'd also mention we're not looking to replace what the SQL plugin is doing in terms of like the parser and use DataFusions. Like we are just going to use what exists today. Not yet. This is all open source, OpenSearch.
Yeah.
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 I think I saw one from over here. Or maybe the light's just too bright. Ah. Sorry, I didn't hear what you said.
Yeah. Using DataFusion as analytics. Yeah, that is actually
Yep.
what it's good for.
So the idea is you store it in a database and you use it effectively to like consume data out of that data source.
Yeah.
Right? Did I explain?
Yeah, actually, DataFusion's pretty cool on its own. So this is where obviously perhaps controversial to say at OpenSearchCon, but if you just forget about OpenSearch and just use DataFusion directly, you can actually do some pretty neat stuff with it. It does very well for OLAP benchmarking. There's the TPCH benchmarks as like one of the standard OLAP benchmarks. DataFusion does really well on the TPCH, and what's the other TPC? I don't remember. Anyway, but yes, so you can use it to query data, say, stored in Parquet. If you have a bunch of Parquet data and you just throw DataFusion at it, it'll rip through it really nicely. Yeah.
So you have to configure, like when you wire it up, how you want your data stored, right? It's not like just wiring in some off-the-shelf thing. And
Yeah.
The data is coming in just data for the day issue. Tomorrow also we register the data. And then when we are querying, which is again more tools, we need to always query and then do the result.
So stored somewhere. Oh, yeah, no. So DataFusion generally doesn't store anything. It is a query engine more than anything. Yeah. Yeah, and that's where theoretically you could imagine something where you build something on top of that, where you add your own kind of materialized view kind of concept, right? Like you could do something where it's like, oh, I have some Parquet files, I'm going to query them, I want to return that as part of like a report or something, but if I've got some intermediate data, you can then take that arrow stream and write it back as Parquet, right? And so, yeah, you could do some materialization yourself without too much difficulty, but yeah, you would have to do that. Yeah.
Is it the same question follow up on the way to just manage the plan
Yeah, we can't really comment on that.
This is all really exciting. How can I help contribute to this?
Thank you. Person I've never met before. Please start with these RFCs and voice your opinion, and we'd love your help. But yeah, there's maybe 3 or 4 RFCs with different slices of this out in the repo, from like adding a query planner, join specifically, support for multiple data sources. So anywhere that interests you, like we'd love to help.
Yeah, I would argue that one of the biggest challenges that we have with this is figuring out where exactly to hook it in, right? OpenSearch as it currently exists doesn't offer a huge amount of flexibility in terms of like where this would fit in naturally. We've discussed various options about like, should there be different internode APIs? Like, should we, break away from the existing OpenSearch transport actions and just have something that, DataFusion talks to DataFusion and then you have some in-process thing? Yeah, that's, if anyone has suggestions on where to hook it in, that would be great. Oh, Marc does.
That's, yeah, a little bit more implementation detail that's on the RFCs, but yeah.
Yeah.
And I don't know if we were clear about this. We want this to be pluggable, right, and opt-in. So that's the challenge. Kunal.
So this sounds a lot like predicate SQL, right? So I have 2 questions. Number 1, does this replace at some point of the future SQL plugin?
No.
And so the example you gave basically around where you have maybe 2 levels of coordinators. It sounds a lot like a multi-case aggregation. One aggregation along the way, and more coordinators. Why would it not replace the SQL plugin? Because the SQL plugin is the same, but you have only one point of one node in the entire database.
So a lot of what the SQL plugin's doing, though, is around parsing and planning. I would argue that the execution in the current SQL plugin is not where the bulk of the logic is. This would sort of be we believe, better way of doing the execution part for the SQL plugin. But yeah, the remaining parts, like obviously something like doing a distributed plan is not something the SQL plugin currently does, right? But that's something where we would certainly hope that folks who know the SQL plugin very well would be able to come up with these distributed plans, for example. Yeah.
Any more?
Oh, Charlie?
Oh.
So I'm wondering, while you made the decision with DataFusion, how do we estimate the efficient loss caused by GNI?
Yeah. So Charlie's question was about the cost of the JNI calls between DataFusion and Java.
Yeah, we found it to be a non-issue. Like, it was minimal, yeah.
Yeah. So I remember discussing this with Navneet regarding the face plugin, or the face implementation for KNN. And that I was saying, like, oh, well, we're using JNI to call into face. Don't we pay, a big JNI cost? And yeah, Navneet was telling me, it's like, no, actually nowadays JNI is really good. Like, it's, that he was saying like microsecond type latencies. So, yep.
DataFusion coexisting with Lucene as agents, and then use DataFusion for some queries and Lucene for other queries?
So, in terms of using DataFusion for some queries versus Lucene for others, so I would see a lot of cases where Lucene does the bottom layer of querying the index and then feeds into we read that into Arrow, which then gets fed into DataFusion. Where I would bypass Lucene or make it complementary would be sort of something like this. So if you have Parquet, DataFusion handles Parquet natively. And so, you avoid an extra J and I hop, right? If you just have, and this would be something where, if you have a Parquet file and then you construct a Lucene index from that Parquet file, so you want to be able to do full text search on your Parquet. And then, you run your full text search, get back some doc IDs, which ultimately would be row IDs, right? And then you could push those down as part of a predicate, as you read Parquet. Yeah. Anthony?
Is this related to the streaming aggregations pull request?
Yes, so Anthony's question is this related to the streaming aggregations pull request? Yes. So this is where, if I recall correctly, that's a pure Java implementation. And that's where the work was connected, and we were sort of saying like, okay, we believe that at scale we start to get benefit from DataFusion, but we were like, what if we just do kind of the bare minimum? Because DataFusion's giving you stuff, but then Arrow's giving you stuff. And so that streaming aggregations is like, what if it's just Arrow without DataFusion? And it does help. So, yeah.
And that is the talk on Arrow, actually, that Mike linked earlier.
Yeah.
I think tomorrow?
Tomorrow, yeah.
They'll go into more detail of that.
Yeah, definitely check out Vamsi and Saurabh's talk. Yeah.
All right. Thank you.